Hello friends, I welcome you all to the video lecture series of cybersecurity and information security. In this lecture, we will study about modes of operation of block ciphers. So now let us start. Firstly, I will tell you about block cipher. A block cipher takes a block of plain text bits and generates a block of cipher text bits, generally of same size. The size of block is fixed in the given scheme. The choice of block size does not directly affect to the strength of encryption scheme. The strength of cipher depends on the key length. Now I will discuss the different modes of operation of block cipher. There are 5 confidential modes of operation for use with an underlying symmetric key block cipher algorithm. ECB, that is electronic codebook mode. Cipher block chaining, CBC mode, cipher feedback mode, CFB, output feedback mode, OFB, and the counter mode, CTR. These are procedure rules for a generic block cipher. The different modes result in different properties being achieved, which add to the security of the underlying block cipher. Electronic Code Book ECB mode. It is the simplest mode of encryption. Each plaintext block is encrypted separately. Similarly, each cipher text block is decrypted separately. Thus, it is possible to encrypt and decrypt using many threads simultaneously. In this mode, the created cipher text is not blurred. The electronic codebook mode ECB is defined as follows. In ECB encryption, the forward cipher function is applied directly and independently to each block of the plaintext. The resulting sequence of output blocks is the ciphertext. In ECB decryption, the inverse cipher function is applied directly and independently to each block of the ciphertext. The resulting sequence of output blocks is the plaintext. In ECB encryption and ECB decryption, multiple forward cipher functions and inverse cipher functions can be computed in parallel. In the ECB mode, under a given key, any given plaintext block always gets encrypted to the same cipher text block. If this property is undesirable in a particular application, the ECB mode should not be used. Now we come to the operation. The user takes the first block of plaintext and encrypts it with the key to produce the first block of ciphertext. He then takes the second block of plaintext and follows the same process with same key and so on so forth. The ECB mode is deterministic, that is, if plaintext block P1, P2 till PM are encrypted twice under the same key, the output ciphertext blocks will be the same. In fact, for a given key, technically we can create a codebook of ciphertext for all possible plaintext blocks. Encryption would then entail only looking up for required plaintext and select the corresponding ciphertext. Thus, the operation is analogous to the assignment of code words in a codebook and hence gets an official name. Electronic Codebook Mode of Operation ECB. Analysis of ECB mode. In reality, any application data usually have partial information which can be guessed. For example, the range of salary can be guessed. A ciphertext from ECB can allow an attacker to guess the plaintext by trial and error if the plaintext message is within predictable. For example, if a ciphertext from the ECB mode is known to encrypt a salary figure, then a small number of trials will allow an attacker to recover the figure. In general, we do not wish to use a deterministic cipher and hence the ECB mode should not be used in most applications. Cipher block chaining, CBC mode. The CBC mode of encryption was invented by IBM in 1976. It is about adding XOR each plain text block to the ciphertext block that was previously produced. The result is then encrypted using the cipher algorithm in the usual way. Each subsequent ciphertext block depends on the previous one. The first plaintext block is added XOR to a random initialization vector. The vector has the same size as a plain text block. If one bit of a plain text message is damaged, then all subsequent ciphertext blocks will be damaged and it will be never possible to decrypt the ciphertext received from this plain text. As opposed to that, if one ciphertext bit is damaged, only two received plain text blocks will be damaged. A message that is to be encrypted using the CBC mode should be extended till the size that is equal to an integer multiple of a single block length, similarly as in the case of using the ECB mode. CBC mode of operation provides message dependence for generating ciphertext and makes the system non-deterministic. In CBC encryption, the first input block is formed by exclusive ORing the first block of plain text with the initialization vector IV. The forward cipher function is applied to the first input block and the resulting output block is the first block of ciphertext. This output block is also exclusive ORed with the second plaintext data block to produce the second input block, and the forward cipher function is applied to produce the second output block. This output block, which is the second ciphertext block, is exclusive ORed with the next plaintext block to form the next input block. Each successive plaintext block is exclusive ORed with the previous output cipher text block to produce the new input block. The forward cipher function is applied to each input block to produce the ciphertext block. In CBC decryption, the inverse cipher function is applied to the first ciphertext block and the resulting output block is exclusive ORed with the initialization vector to recover the first plaintext block. The inverse cipher function is also applied to the second ciphertext block and the resulting output block is exclusive ORed with the first ciphertext block to recover the second plaintext block. In general, to recover any plaintext block except the first, the inverse cipher function is applied to the corresponding ciphertext block and the resulting block is exclusive ORed with the previous ciphertext block. In CBC encryption, the input block to each forward cipher operation except the first depends on the result of the previous forward cipher operation. So, the forward cipher operations cannot be performed in parallel. In CBC decryption, however, the input blocks for the inverse cipher function, that is the ciphertext blocks, are immediately available so that multiple inverse cipher operations can be performed in parallel. Analysis of CBC mode. In CBC mode, the current plaintext block is added to the previous ciphertext block and then the result is encrypted with the key. Decryption is thus the reverse process which involves decrypting the current ciphertext and then adding the previous ciphertext block to the result. Advantage of CBC over ECB is that changing initialization vector results in different ciphertext for identical message. On the drawback side, the error is transmission gets propagated to few further blocks during decryption due to changing effect. It is worth mentioning that CBC mode forms the basis for a well-known data origin authentication mechanism. Thus, it has an advantage for those applications that require both symmetric encryption and data origin authentication. Cipher feedback mode CFB. The cipher feedback mode CFB is a confidentiality mode that features the feedback of successive ciphertext segments into the input blocks of the forward cipher to generate output blocks that are exclusive odd with the plain text to produce the ciphertext and vice versa. The CFB mode requires an initialization vector as the initial input block. The initialization vector need not be secret, but it must be unpredictable. The CFB mode also requires an integer parameter denoted S such that S is within 1 and B. In this specification of the CFB mode below, each plaintext segment and ciphertext segment consists of S bits. The value of S is sometimes incorporated into the name of the mode. Example, the 1-bit CFB mode, the 8-bit CFB mode, the 64-bit CFB mode, or the 128-bit CFB mode. In CFB encryption, the first input block is the initialization vector and the forward cipher operation is applied to the initialization vector to produce the first output block. The first ciphertext segment is produced by exclusive ORing the first plaintext segment with the S most significant bits of the first output block. The remaining B minus S bits of the first output block are discarded. The B minus S least significant bits of the initialization vector are then concatenated with the S bits of the first ciphertext segment to form the second input block. An alternative description of the formation of the second input block is that the bits of the first input block circularly shift S positions to the left and then the ciphertext segment replaces the S least significant bits of the result. The process is repeated with the successive input blocks until a ciphertext segment is produced for every plaintext segment. In general, each successive input block is enciphered to produce an output block. The S most significant bits of each output block are exclusive odd with the corresponding plain text segment to form a ciphertext segment. Each ciphertext segment except the last one is fed back into the previous input block as described above to form a new input block. The feedback can be described in terms of the individual bits in the strings as follows. If I1, I2 till IB is the jth input block and C1, C2 till C is the jth ciphertext segment, then the j plus 1th input block is IS plus 1, IS plus 2 till IB. In CFB decryption, the initialization vector is the first input block and each successive input block is formed as an FB encryption by concatenating the B minus S least significant bits of the previous input block with the S most significant bits of the previous ciphertext. The forward cipher function is applied to each input block to produce the output blocks. The S most significant bits of the output blocks are exclusive odd with the corresponding ciphertext segments to recover the plain text segments. In CFB encryption, like CBC encryption, the input block to each forward cipher function depends on the result of the previous forward cipher function. Therefore, multiple forward cipher operations cannot be performed in parallel. In CFB decryption, the required forward cipher operations can be performed in parallel if the input blocks are first constructed from the initialization vector and the ciphertext. The output feedback mode, that is OFB. The OFB mode is the confidentiality mode that features the iteration of the forward cipher on an initialization vector to generate a sequence of output blocks that are exclusive odd with the plaintext to produce the ciphertext and vice versa. The OFB mode requires that the initialization vector is a nonce, that is, the initialization vector must be unique for each execution of the mode under the given key. The OFB mode is defined as: in OFB encryption, the initialization vector is transformed by the forward cipher function to produce the first output block. The first output block is exclusive OR with the first plaintext block to produce the first ciphertext block. The forward cipher function is then invoked on the first output block to produce the second output block. The second output block is exclusive OR with the second plaintext block to produce the second ciphertext block, and the forward cipher function is invoked on the second output block to produce the third output block. Thus, the successive output blocks are produced from applying the forward cipher function to the previous output blocks, and the output blocks are exclusive OR with the corresponding plaintext blocks to produce the ciphertext blocks. For the last block, which may be a partial block of U bits, the most significant U bits of the last output block are used for exclusive OR operation. The remaining B minus U bits of the last output block are discarded. In OFB decryption, the initialization vector is transformed by the forward cipher function to produce the first output block. The first output block is exclusive OR with the first ciphertext block to recover the first plaintext block. The first output block is then transformed by the forward cipher function to produce the second output block. The second output block is exclusive OR with the second ciphertext block to produce the second plaintext block, and the second output block is also transformed by the forward cipher function to produce the third output block. Thus, the successive output blocks are produced from applying the forward cipher function to the previous output blocks, and the output blocks are exclusive OR with the corresponding ciphertext blocks to recover the plaintext blocks. For the last block, which may be a partial block of U bits, the most significant U bits of the last output block are used for the exclusive OR operation. The remaining B minus U bits of the last output block are discarded. In both OFB encryption and OFB decryption, each forward cipher function depends on the results of the previous forward cipher function. Therefore, multiple forward cipher functions cannot be performed in parallel. However, if the initialization vector is known, the output blocks can be generated prior to the availability of the plaintext or ciphertext data. The OFB mode requires a unique initialization vector for every message that is ever encrypted under the given key. If contrary to this requirement, the same initialization vector is used for the encryption of more than one message, then the confidentiality of those messages can be compromised. In particular, if a plain text block of any of these messages is known, say the jth plain text block, then the jth output of the forward cipher function can be determined easily from the jth ciphertext block of the message. This information allows the jth plaintext block of any other message that is encrypted using the same initialization vector to be easily recovered from the jth ciphertext block of that message. Confidentiality may similarly be compromised if any of the input blocks to the forward cipher function for the encryption of a message is designated as the initialization vector for the encryption of another message under the given key. The counter mode, that is CTR. CTR mode is the confidentiality mode that features the application of the forward cipher to a set of input blocks called counters to produce a sequence of output blocks that are exclusive OR with the plain text to produce the cipher text and vice versa. The sequence of counters must have the property that each block in the sequence is different from every other block. This condition is not restricted to a single message. Across all of the messages that are encrypted under the given key, all of the counters must be distinct. In this recommendation, the counters for a given message are denoted T1, T2 till Tn. Methods for generating counters are: given a sequence of counters T1, T2 till Tn, the CTR mode is defined as follows. In CTR encryption, the forward cipher function is invoked on each counter block and the resulting output blocks are exclusive ORed with the corresponding plain text blocks to produce the cipher text blocks. For the last block, which may be a partial block of U bits, the most significant U bits of the last output block are used for the exclusive OR operation. The remaining B minus U bits of the last output block are discarded. In CTR decryption, the forward cipher function is invoked on each counter block and the resulting output blocks are exclusive ORed with the corresponding ciphertext blocks to recover the plaintext blocks. For the last block, which may be a partial block of U bits, the most significant U bits of the last output block are used for exclusive OR operation. The remaining B minus U bits of the last output block are discarded. In both CTR encryption and CTR decryption, the forward cipher functions can be performed in parallel. Similarly, the plain text block that corresponds to any particular ciphertext block can be recovered independently from the other plain text blocks if the corresponding counter block can be determined. Moreover, the forward cipher functions can be applied to counters prior to the availability of plain text or ciphertext data. So friends, this was all about modes of operation of block ciphers. Hope the concepts explained in this lecture were understandable and helpful. Hope to see you in next lecture. Till then, goodbye. Thank you.